The way that weight changes is just one example of Newton's famous equation in action. But Newton had left his masterpiece incomplete. He didn't know the value of G, the gravitational constant, which sets the size of the force. To harness the full power of the equation, you need to know G. And the vital clue came with an incredible experiment conducted in London at the end of the 18th century. It was an attempt to work out the mass of the Earth itself. And it was carried out by an eccentric, extravagantly rich aristocrat, Henry Cavendish. Cavendish was a chronically shy, deeply solitary man living in total isolation in his house in Clapham. The story goes that one day he accidentally bumped into a female servant on his staircase. He was so traumatized by this event that he had a new staircase built just for him, so this horrible incident could never happen again. Cavendish had inherited vast fortunes and was able to dedicate his life to devising pioneering experiments, including one particularly extraordinary piece of equipment. He set up something a bit like this. It's called a torsion balance. It involves 4 lead spheres, 2 large heavy ones which are held fixed in place, and suspended by a very thin wire is a wooden rod, 6 feet long, with 2 smaller balls on either end. Now, the crux of the experiment is the relationship between the large ball and the small ball. Now, of course, there's a gravitational pull downwards on both of the balls due to the Earth's gravity. But Newton also tells us that there should be a very weak gravitational pull between the balls. And this is effectively what Cavendish was trying to measure. Any slight movement of the small ball towards the large one should cause a twist in the torsion wire. And that's what Cavendish was trying to detect. Of course, this is all much easier said than done. The experiment was incredibly sensitive. The tiniest of vibrations, the slightest breeze, changes in temperature could all influence the measurements. So Cavendish had to isolate the apparatus inside a box and the box within a shed. He even realized that his mere presence next to the apparatus could influence things, so he had to remove himself outside the shed. What he then did was sit outside the shed and through a small hole in the shed wall, look through a telescope to detect the tiniest of twists in the wire. It was an incredibly difficult process, but after many months, he finally felt confident enough that he had a reliable result. Cavendish found that the small balls did move. A tiny 4 millimeters. He calculated his results by comparing the density of the balls with the density of water. In the end, the result of Cavendish's experiment and subsequent calculations was that the density of the Earth was about 5.5 times that of water. Or, put another way, the mass of the Earth was 5.9 trillion kilograms. What's most remarkable is that Cavendish got this number right to within an accuracy of 1%. With Cavendish's astonishing result, scientists were able to work out G. Then the equation could be used to determine the mass of any celestial body in orbit around another. So astronomers were able to calculate the mass of the Sun and the planets and the Moon, and eventually even distant galaxies. And of course, back on Earth, we never escape gravity. Over the course of the day, it actually squeezes your spine, an effect you can see for yourself if you use a measuring rod. Okay, so it's 7:30 in the morning. I've just got up and I'm going to see how tall I am before gravity drags me down. That's 178 centimeters, or just over 5'10". Over the course of the day, gravity compresses the fluids in your spine. Right, it is just past 11 p.m. I've been standing up for most of the day, so let's see if gravity has had an effect on my height. That is 176 centimetres, so I really have shrunk by just over ½ an inch over the course of today. In the longer term, gravity can affect your posture permanently. But there are exercises you can do to counteract this effect.
Part of my research has been looking at the effects of gravity on the human body. So people might not be aware, or they might not always think about the effect of gravity on our physical state, on our health, and particularly on our posture. However, because it's such a constant force, gravity has a massive impact over the course of our lifetime.
As you get older, you can develop a stoop, which is damaging to your mobility.
Gokul here has actually got very good posture, but I'd like you to just show not so good posture. So when poor posture is really rounded shoulders and then loss of the curve in the back as well. I can't just ask you to raise up your arms when you're in that posture. So, no, and then just come back down, shoulders back into normal, and then raise your arms. You can see the effect of posture on function.
Ironically, the exercises which many gym goers do actually make your posture worse. That's if you only exercise the frontal muscles, like the chest and abdominals. So it's recommended you exercise the back muscles just as much, to straighten you out and counteract the effects of gravity.